All right, let's get started. Okay, so last day of class. The final is a week from tomorrow in here. It will cover the entire semester. You can bring 2 sheets of notes, but no calculator. Bobby King is going to do a review tomorrow from 10:30 to 12. We will record it and post it for those of you that can't make that time. But it's in here starting at 10:30. If you have any pending grading issues that we haven't dealt with, remind us. So far we've graded our release grades all through PS10. We still got a little bit to work on PS11, and then we got our grade PS12. But could be worse. Any questions or problems? Okay, so what I propose to do to start is to just go over the sample final exam, and we can work it together, and you can ask any questions about the problems or anything that occurs to you while we're looking over them. So what about this first one here? This is you pretty much count on the question about the master theorem, but how do you approach this? Remember? Yep.
So I know in the midterm you gave us the master theorem. Are you going to put it on the final again?
Yeah, it'll be on the final. Yeah. Who wants to take a crack at this? Yeah.
So the A, B, and C or D, whatever it is, just take 3, 2, and
Okay. So right here we got A is 8, B is 3, D is 2. And what's log base B of A? Yep.
I just want to ask, are you recording?
Yes, I'm recording. Good. Since you asked, I will make sure. Yep, we're going. Thank you. So what's log base B of A? Yeah?
less than 2.
Less than 2 is all that matters. You figure if it was 9, it would be 2. 3 squared is 9, so it's less than 2. So D is bigger. And so the answer is just O of n squared. Okay, what about the next one? Well, what are A and B? 9 and 3. So what's log base 3 of 9? I just said that was 2. So 2, and then we got to put a big O bound, a polynomial bound, a pure polynomial bound on O of n log n. So what's a D that would work? Yeah.
7 less than 2. Okay.
Yeah, anything bigger than 1 will work. In particular, there are lots of things less than 2 that will work. 1.5, 1.1, 1.01, whatever. So we can certainly find a D that's less than 2. So again, our answer is O of n squared. What about the next one? So A is 1, B is 2. So what's the log base 2 of 1? 0. And then D is 0 as well. O of n to the 0 is the bound. So those are the same. And so that's the case where the answer is going to be n to the D log n. N to the D is just 1. So O of log n. If I make a mistake, be sure and let me know, because I'm not looking at any notes. What about the final one? So want to explain how to do it? Yep.
It's log base 2 of 2, which is 1,
Mm-hmm.
which is greater than 0.
Right.
And I think if I remember, that means we have log base B of A, like O of log base B of A, or
Yeah.
n to the log base B of A.
Yeah.
Yeah.
So it's just O of n. So log base 2 of 2 is 1, and 1 is bigger than the d, which is 0. So it's O of that n to that 1, which is just O n. Okay? So this also, the final will have 25 questions, and sometimes there'll be multiple parts. Each one will be worth 4 points. And more so on the final than on the midterm, I make sure that they're easy to grade. So it'll be really, short answers, nothing really long you'll have to write. This final may be different, it's fairly old, but. Okay, any questions about that? Okay, so here's a question about RSA, public-private key pairs. So we've got to, we start with 2 prime numbers, 5 and 13, and we've got to answer questions. So what is n? Okay, it's 13 times 5, which is 65. And what's the smallest possible value you could use for e? So what property does e have to have?
It's not in the group. It's not in the group.
Well, what group?
The group of n, like. Sorry,
What do you have to figure out before you figure out n? Before you figure out e?
phi.
Yeah, you got to figure out phi. And I didn't ask that, but what is phi?
40 times 12.
4 times 12, which is 48. Okay, so now what property does e have relative to phi?
It has to be co-prime.
Right, it has to be relatively prime to phi. And we want the smallest one. So 2 won't work, 3 won't work, because that's a multiple of 3 we're looking at. 4 won't work, 5 will. So the answer would be 5. Okay, so if that is what E is, what is D? What property does D have to have? Yeah.
D is the multiplicative inverse of E mod B.
Okay, so we got to have that ED is equal to 1 mod phi, and what we got, E is 5, so we got to have 5 times D is equal to 1 mod phi. So we got to find the inverse of 5 mod phi. So what can we multiply 5 by to get something that's 1 more than a multiple of phi? So this is kind of pushing the limit of what you can do without a calculator. But let's see if we can do it anyway. So how could you find, sitting on an exam, you could sit down and try to run, try to simulate the algorithm for modular multiplicative inverses, but what's another way to think about it? Yep.
Keep multiplying, or keep adding 48 together until you get something that ends with a 4 or a 9.
Right. We look at multiples of 48 till you find one that's 1 less than a multiple of 5. So let's see, we got 48 and then 96, and what will be next? We add 48 to that, we get 144. Okay, that's 1 less than a multiple of 5, so we just have to figure out what 145 divided by 5 is. $29. I do that right? All right, so the answer is 29. I think this exam I allowed a calculator. So. And then it asks, what's the result of encrypting 3? Good thing I didn't ask about encrypting. Good thing E is just 5. So how do I figure out the result of encrypting 3?
3 to the 5 mod n.
Right, so it's just 3 to the 5th mod 65. And let's see, what's 3 to the 5th? 3, 9, 27, 81, 243? So it's 243 mod 65. And we just got to do the division and get the remainder. Someone do that for me, I'm too tired.
48.
48 is the answer?
Yes.
Okay, yeah, that's a slog. If I ask a question like that, I'll use smaller numbers. Okay, any questions about that? Okay, so we're supposed to come up with a recurrence relation to describe the running time of that method there. So take a minute and look at it. I mean, we got the base case here. If the array is of length 1, it says A is non-empty, so that's important. And here's the recursive case. So we can certainly do the base case. That's constant, so. What's it take to figure out the recurrence relation for the general case? Yeah.
There's two recursive calls that subdivide the over to half. So you have 2 times t n over 2.
I'm looking for the, okay. Right, so you're making 2 recursive calls. And we got to look at how big the, so certainly there are 2 recursive calls, so we can start with 2t. How big are the arrays that we pass? So A1 and A2, how big are they compared to A? Okay, so you can see right there, it's A dot length, it's half there, and this is half. Give or minus 1, plus or minus 1. So there, okay, we got that part. And then what's the overhead? How much work are we doing to besides the recursion? Yeah, I mean, so the math dot min is something that's constant, but the main work is allocating those arrays and filling them in, which involves loops that are proportional to the lengths of the arrays, which is n. Okay? Questions about that? Yeah.
I have a hard time associating how A2 is equal to half A dot length.
Well, if A1 is half the length of A,
Yeah.
then A2 will be the length of A minus, oh. Wow. Oh, okay.
Yeah, still.
I was looking for A1 dot
Oh
length.
yeah, okay. I was also looking at A1. Sorry. Yes.
Yeah, I was looking for A1 dot length, but I've got A dot length divided by 2.
Yes.
Thanks. So when you're doing this, what can you ignore? I wonder if students get tied up in stuff that doesn't matter. What does it really matter when you look at this method? And the for loops matter because that's where the overhead comes from. Yeah.
I don't think it really matters like what this is actually doing.
Right. It doesn't matter what it's doing. So don't waste any time trying to figure out what's it actually computing. It's just, it's computing something. Your problem is to determine how long it takes. So don't worry about, you know, why we're splitting the array in half and what it would do and what it would return. Just worry about how long it takes to do it. Okay, let's see what's next. True, false. The metagraph obtained by running the strong intent components algorithm will always have a single source and a single sink. So you're given a directed graph. You run the strong intent components algorithm. You get a metagraph out. Will it have a single source and a single sink? So I think I told you before, but one of my heuristics for true false is I just try to think of a counterexample. Right? So, can you think of a counterexample to this assertion? Yeah.
2 nodes that point at 1 node.
Okay. So he has basically a DAG that looks like this. 2 vertices that lead to 1 vertex.
That's for multiple sources but 1 sink.
Right. And that's a DAG, and if you remember that when you run it through the SEC algorithm on a DAG, you just get the thing back, you get the DAG back. And if there's 2 sources going in or 2 sources going back, coming back, or if you don't remember that fact, you just look at that and realize it has 3 sine components. And it certainly has 2 sources. Is there always 1 sink? No, we could add a couple more arrows out and or even simpler, we could just have a graph with 2 vertices and no edges, and then you've got the SCC has yeah, 2 sources and 2 sinks. Yeah.
There's something one strongly connected component. Is it both a source and a sink?
Yeah. So if your SCC looks like just a single vertex, then yeah, that's both a source and a sink. All right, so the answer to this is false. Okay, following a depth first search, it is possible for 1 vertex to have pre-post times of 517, and another vertex to have pre-post times of 10/28. Wow, what a question. I must have thought that was a good idea at some point. Okay, how would you approach this? I'm trying to figure out how I would approach it. Yeah?
Whether or not it's possible that something can have a lower pre and post time than something with a higher pre time.
Okay. So look at the relative, that's what I would look at first as well, is the relative values of these things. So we're doing the depth first search. We got to the first vertex at time 5, so we reached it first. And then, before we finished with that vertex that we visited first, we visited this other vertex at time 10. But then we somehow finished up the original vertex before we finished up the second vertex. Okay? Can that happen with depth first search?
No.
No, you're gonna, if you encounter something first and then something later, you're gonna finish up the later one before you finish up the first one. Or another way to think about it, if you happen to have memorized the patterns you can get with forward edges and back edges and such, this isn't one of the allowable patterns of pre and post times of 2 edges in a depth first search. But I don't have those memorized. I just would reason that out. Now, if it had said 5, 17, and if the second one had been 10, 15 or something, then it probably would be possible, I guess. But this one is clearly impossible. Okay, the depth first search algorithm may fail to visit every vertex. So this is where it's important to distinguish between depth first search and explore, which is something depth first search calls. So what if the question was, the explore algorithm may fail to visit every vertex? That's true. Explore starts at a vertex and visits everything it can reach, which may not be every vertex in the graph. But why, when it says a depth first search algorithm may fail to visit every vertex, why is that answer false? Yeah?
Because it's specifically meant to look for vertexes after it's done creating its first search.
Yeah. It just runs a loop and it keeps going until it's visited every vertex. So there we have the rare true-false question where all the answers are the same. I can imagine this. I don't know if I did this deliberately or not. It could make you uncomfortable, right? Start to second guess. I can't tell you how many students I've had in my office over the years saying, I had the right answer and then I changed it. But then I guess students don't come in to me to say, oh, I had the wrong answer and then I changed it. So I don't know what the lesson is, but Lots of students have realized they shouldn't have second-guessed themselves. Okay, here's some more true-false questions. There is a graph such that when Dijkstra's algorithms and Prim's algorithm both started at the same vertex, the first edge chosen by Dijkstra's algorithm is different from the first edge chosen by Prim's algorithm. Okay, first of all, what problem does Dijkstra's algorithm solve? Shortest path. And what about Prim's algorithm? That's minimum spanning tree. So they're different algorithms. So what's the answer here? What's the first edge that Dijkstra's algorithm would pick? The lightest edge out of the start is what it picks first. Okay? And what about Prim's algorithm? So remember, Kruskal's is the one that does the just picks the lightest edge in the whole graph, and then it keeps picking the lightest edge. It doesn't create a cycle. So this is Prim's algorithm, which is sort of like Dijkstra's algorithm. So you sort of have to think about the difference in implementation of the algorithms. And what was really the only difference? What was the rule that Prim's algorithm used to pick an edge each time?
Yeah, just the lightest edge in general.
Well, no, that's Kruskal's is picking the lightest edge that doesn't form a cycle. Well, let's talk about Dijkstra's. Dijkstra's is picking the lightest edge. At any given point, it picks the edge to a vertex on the fringe that is closest to the root. Because it's trying to do a minimum spanning tree. Okay? And Prim's algorithm does a slightly different calculation. Who could characterize that? So Dijkstra's is looking at all the vertices, at a given point, it looks at all the vertices on the fringe, which are the ones on the priority queue, and picks the one that's closest to the root. Prim's looks at all the vertices on the edge, on the fringe, and looks for the one that's closest to any vertex that's already in the tree. Because Prim's is trying to grow a minimum spanning tree. So to draw a picture, if this is the tree you've grown so far, and here's the fringe, Dijkstra's algorithm is looking for the one that's closest to the root. Prim's algorithm is looking for the one that's closest to any of these, to any vertex. Okay, so that's the difference. So when you're looking for the first edge, will there be any difference? Right. The vertex is closest to the root, but there's only one vertex in the tree, which is the root. The vertex that's closest to the root is also going to be the vertex that's closest to any vertex in the tree, since there's just one. So that would be false. Okay. There's a graph for which the Bellman-Ford algorithm will perform fewer update operations than Dijkstra's algorithm.
Not true if you have like negative edges.
It's a good question. Let's try to do it without negative edges. Yep. Oh, great. Okay, yeah. So it says all the weights are positive, so no negative edges. Well, what's the minimum number of edges that Bellman-Ford has to update? What's the least it could get by with? Well, if there are V vertices and E edges, what does Bellman-Ford do? It makes a number of passes. It looks at all E edges, updates them all, and then does it again, and so on. What's the soonest? How many passes does it have to do at minimum? 2 passes. So it's going to do 2 E updates at a minimum. Okay? How many updates does Dexter's algorithm do? No, think about the algorithm. Yeah. Hmm? No, it's more than V. Yeah, it's E. Basically, it loops. Each time, there's sort of an outer loop that picks a vertex off this priority queue. And then it looks at every edge out of that vertex and potentially updates it. It considers it for an update. So at most it's going to do E. So even I'm getting uneasy right now, but all the answers are false. I must have been in a perverse mood when I made this decision. Okay. There's a graph such that the total weight of the edges found by the Bellman-Ford algorithm can be less than the total weight of the edges found by Kruskal's algorithm. Okay? Okay, so what's Bellman-Ford algorithm finding? It's finding shortest path tree. Let's see. Okay, they're all connected, so that's important to know. Yeah, this is all really crucial. It's undirected, connected, and weighted. So Bellman-Ford is finding a shortest path tree. But that's also a spanning tree, right? Because it hooks all, it's going to hook all the vertices together into a tree. So that's a spanning tree. Kruskal's finding a minimum spanning tree. And we're asked, is there a graph such that the total weight of all the edges found by Bellman-Ford can be less than the total weight of all edges found by Kruskal's? Okay, Kruskal's found a minimum spanning tree. So the total weight of all the edges in the tree found by Bellman-Ford can't be less than that of a minimum spanning tree. Yeah?
So, what's the difference between these two algorithms, between the minimum spanning tree and short?
Okay. So let's talk about the difference between a minimum spanning tree and a shortest path tree. Okay? Who could tell me a tree where the answer is different for the two? Let's draw a tree where the minimum spanning tree has a different weight from the shortest path tree. Yep.
Didn't you just do just a regular binary tree?
Well, if we start with a regular binary tree, there's only one tree that can be drawn. That's the. So,
Right. Wouldn't the minimum spanning tree just be the whole tree at that point?
yeah, but I'm looking for a case where the trees are different. Okay, so instead of asking that question, let me just draw you a graph here. Okay, so 1, 2, 1, 1, 3, 1, 4, 2. Okay, so if we run Kruskal's algorithm starting at this vertex right here, not Kruskal's algorithm, Bellman, no, forget that. Bellman-Ford, neither one has a starting point. We run the algorithm. It's going to find a minimum spanning, it's going to find a shortest path tree if we run Bellman-Ford. Okay, so that tree is going to contain in it the shortest path between a start vertex and any other vertex. Okay, so what would the shortest path tree be for this here? It's going to start here. What's the shortest path to this? I wish I'd labeled them. The left vertex on the second level. All right, it's going to be here. What's the shortest path to the next one on the second level? Okay. What's the shortest path to the third one on the second level? In other words, this one here, I guess on level 2.5. the shortest way is that way. Okay? What's the shortest path to here? That one. Okay? What about the shortest path to here? That's going to be that way. And let's see, where are we? The shortest path to here is going to be, did that one, shortest path to here. It's going to be that path of length 5, right? Okay, so that's a minimum spanning tree. It encodes within it the shortest path from the root to any other vertex. So to find out that path, you just start at the vertex, and there's going to be one way to go back to the root. And so the shortest path from here back to there has weight 8. Oh, weight 5. Yeah, I wrote the weight instead of the 2 here. Okay. Now, a minimum spanning tree is a tree that connects all the vertices together, and what you're trying to minimize is not the distance back to the root from every vertex. You're trying to minimize the sum of all the weights on the edges. Now, this may well also be a minimum spanning tree. Can you think of a different way of hooking all the vertices together into a tree? Yeah.
So instead of using the 2 on the right, you use the 1 that's in the middle below. So
Okay, so instead of using this edge here,
yeah, you use the connecting the 1.
this edge here,
Yeah, that one.
which I didn't,
Didn't really label.
we'll call that a 1 as well. Okay, so what he's saying is this edge right here, we'll call it weight 1. If we added that in and took this edge out, that's still a spanning tree, but it has less weight than if you add all the edge weights up, that's smaller than the minimum than the shortest path tree had. But this is no longer a shortest path tree. Why? Like, there used to be a path of length 5 from here back to the root. Now there's a path of length 2, 3, 4, 5, 6. So it's not a shortest path tree. Either way, it's a spanning tree. What I originally had here was a shortest path tree. Now I have, hopefully, a minimum spanning tree, unless there's another way to optimize it. So this is an example where the weight of the edges found by Bell and Ford is less than the weight of the edges found by Dijkstra's algorithm. But that's not what's asked. Can the total weight of all the edges found by Dijkstra's algorithm ever be less than the total weight of all the edges found by Bell and Ford? Oh. Okay. Back to the top. There's a okay, so this is the kind of graph that might be found by Kruskal's algorithm. It's less than the total weight of all the graph found by Bell and Ford, but can't be the other way around. Bell and Ford find a graph whose total edge weight was less than that found by Kruskal. No, because Kruskal finds the minimum spanning tree. The trick here, the thing to realize is we're asking for the total weight of all the edges in the tree found by Bell and Ford. That's not something we even care about in Bell and Ford. We're not trying to minimize the total weight of all the edges. We're trying to minimize the length of all the paths. So it's a metric we don't usually apply to Bell and Ford. But since Bell and Ford and Kruskal's will both find a minimum spanning tree if the graph is will find a spanning tree if the graph is connected, Kruskal's not going to find a wider minimum spanning tree. Okay. Any other questions about that? There is a graph such that the total weight of the edges found by Dijkstra's algorithm can be less than the total weight of the edges found by Bell and Ford. It's tricky. They're both going to find shortest paths trees. So the question is, could you have two shortest paths trees which nevertheless had, if you add the total weights up, they're different? Because it's sort of random, both algorithms can make arbitrary choices depending on the order which they consider the edges. So they could produce different shortest paths trees that encode paths of the same length. Could you have ones where the total weights were different?
Wouldn't Bellman Ford create a smaller one because just doing it over and over again, so it's basically optimizing?
No, you can't conclude that it's going to be. So again, both these algorithms are producing spanning trees, and the spanning trees are designed to encode shortest paths. So we're applying a metric we don't usually apply to shortest paths, which is what is the weight when you view them as spanning trees. So you don't really have to think about the details of the algorithm. It's just, is it possible to have a graph with two spanning trees, with two shortest path trees, where the edge weights, the total edge weights are different? Yeah.
I would guess the no, because each node would have to have their minimum distance to each one, and so the distance to get each one to add up, I think it's still the same, right?
Okay, well, let's look at this possibility. Let's have vertex A, vertex B, vertex C in a triangle, and we'll let A to C be 2, and we'll let A be, the other edges be 1. Okay, can you find two shortest paths trees here? Okay, so one shortest path tree would be A to B and A to C, with total edge weight 3. So that's a minimum spanning tree because the shortest path from C back to A is of length 2, no matter how you go. The shortest path from B back to A is 1, no matter how you go. So you get a total weight of 3. What's another minimum spanning tree here? Shortest path tree.
A to B to C.
Yeah, just go A to B to C. And again, the path from C back to A is 2. And the path from from C back to A is 2, and from B back to A is 1, like before. But viewed as a spanning tree, the total weight is 2. Yeah.
So, on your example on the left, if you were to choose for the second vertex going down, and then never mind.
I think these are the only two two shortest path trees. But they have different weights when you add up all the edge weights. And it's entirely possible that Bellman Ford could find one and Dijkstra's the other. It just depends on the flip of a coin at some point. So, someone following along with the answers, if I'm getting these right? Okay. I have to admit that I came at this cold. I didn't study this exam beforehand, and I'm finding this really stressful. So, I haven't taken a test in a long time, but I feel like I'm taking one now. Yeah.
I get another question, but how did you get true on that instead of false? It's not that it was false. Previous one.
Yeah, I mean, I just showed Dijkstra's algorithm could find this tree of weight 2, and Bellman Ford could find this tree of weight 3.
Read that wrong. Thanks.
Yeah.
But just for clarity, both algorithms could have found either of those two
Yeah.
trees.
Yeah, it's nothing special about Dijkstra's. I mean, I could have flipped the order of Dijkstra's, and if Bellman Ford would still be true. It's just depends on random events. Okay. If it were proven that every algorithm for factoring an integer n must be omega n in the worst case, this would imply p equals np, p is not equal to np, neither of the above. This is kind of a deep question. It's not an easy one. Okay, so C is a popular answer, but I don't believe it's right. So let me apply. What would be the reasoning to argue for C? Yeah. Well, no, well, first of all, factoring is not known to be NP. No, it's a member of NP. Maybe. Okay.
That's fine.
All right. So factoring is a known problem that belongs to NP. And we found that it's omega of n. So we found that it takes at least a certain amount of time. So you might look at that and say, okay, we're saying that factoring, if you prove that factoring takes at least linear time, then that doesn't tell you anything about P versus NP. What's the big deal about proving that some algorithm takes linear time? Okay? But that's not saying it takes at least linear time. All n's aren't the same. When you're trying to get to judge the complexity of an algorithm in order to make conclusions about P and NP, what do we care about? What n do we care about? What measure of the input size do we care about? Yeah, the length of the input, the size of the input, the number of bits in the input. So if we're factoring in, what we care about is not the complexity in terms of the integer itself. We care about the complexity in terms of the length of the integer, the number of bits in the integer. How many bits are in this integer n? What's the size of the integer n? It's just log of n. And so what we've found, if we prove this, that factoring is omega of 2 to the log n, where log n is the size of the input, we have proven that factoring requires at least exponential time. Now, once you've proven that factoring takes at least exponential time, what does that say about those three questions there? You've got some algorithm from NP that requires exponential time. So could P equal NP at that point? No, because it can't, because P is only polynomial time algorithms. This would be a proof that factoring is not a polynomial time algorithm. So the answer would be, that's wrong.
You had the right answer then.
Had the right answer and marked it. Yeah, I hear that too. That would be P is not equal to NP. Right, so this is the thing I have repeated over and over during the semester about when you're judging algorithms, you care about the length of the input. And very often, you know, when you talk about that an array of length has length n, you're talking about the length. If you talk about an array has v vertices and e edges, those are related to the length. That's, you know, the amount of bits it takes to represent the graph is related to those. But when you're talking about factoring a number n, the length is log of that number. So don't confuse the magnitude of an integer with its length. Yeah?
I'm a little bit confused because factoring isn't its own NP-complete problem, and there are some NP problems that take exponential time.
Oh.
And some NP problems that don't take exponential time.
No, there are no problems in NP that we know require exponential time. Okay? So the way the world works is, or looks, is this: if this set is NP, some of those problems we know can be solved in polynomial time because we have solved them.
Yeah.
The rest of the problems that aren't inside of P, the best solutions we know for them are exponential. But no one has proven that that has to be the case. That's the whole question of P equals NP. If P equals NP, every problem from NP can be solved in polynomial time. If P is not equal to NP, then some of those problems require exponential time. We don't know the answer to that question.
Oh, so you're proving that an NP problem requires exponential time, so you know it's not.
Right. So factoring right now sort of lies right here. It's not known to be NP complete. It is not known to be a member of P, but for all we know, it could be either one. But if we did this proof, it would tell us that this particular point here in factoring requires exponential time, which would force us to conclude P is not equal to NP. Yeah.
So to get a proof of P equals NP, then you have to prove that a NP complete problem is, you can solve the problem with time pressure.
So that's the most obvious way to prove P equals NP would be to prove that some NP complete problem has a polynomial time output. Yeah.
So if the input n in this case was a greater magnitude and just n to the 1, but the omega was still omega n, would the answer be P equals NP?
I'm not sure. I mean, the input is an integer.
Okay.
So I'm not sure what you mean by something more
It was
than
like n raised to 100 was the input, and it was still omega of n for the worst case. Is it still?
Well, okay, so if you say that you have an algorithm that will factor the number n to the 100th in omega of n time, well, we still got to look at the length of the input, which is going to be log of n to the 100th, which is going to be 100 log n. So it's still going to be exponential. Yeah.
So the conclusion we reached, was it based on an omega of 2 to the log n or an omega of n? That was close.
The omega of 2 to the log n.
But the question is posing for omega of n, right?
Right. If you can factor it out, if factoring requires omega of n, time proportional to the length of the integer, then that's another way to say it is it's omega of 2 to the log n, right? 2 to the log n is the same as n. So those two expressions are saying the same thing. Omega of n, omega of 2 to the log n are saying the same thing. But log n happens to be the size of the input. So this is the one that matters for comparing, for talking about the complexity of the algorithm. Yeah.
So if, for example, it was, instead of exponential, it was actually linear, was that true anything? Or
If we prove that factoring was
or polynomial?
was O of so if we prove that factoring was O of log n to the 5th power, say. So it's if the length of the input is n, the complexity is n to the 5th. Okay, what would that say about P equals NP?
Nothing, right?
It would say nothing, because it would just be yet another problem from NP that we have figured out how to solve in polynomial time. Now, if you then turn around and prove that factoring is NP complete, then that would mean having that fast algorithm for factoring would prove that P equals NP. But we don't know that factoring is NP complete. Yeah.
So you're using, kind of going back to the beginning, but you're using log n because that's how many bits you have to check.
That's the length of the input, the size of the input.
But that's not how many bits, that's just like how many bits you have to check to factor.
No, that's the number of bits required to represent n. So like if n is 1,000,000, log n is 20. It takes about 20 bits to represent 1,000,000. 30 bits to represent 1,000,000,000. Yeah.
Sorry to keep beating this one, but the example you just gave, where you move a problem in NP into NP complete, proves that P does not equal NP?
No, if we did two things. If we proved that factoring is NP complete and showed that we could solve factoring in polynomial time, those two things together would prove P equals NP. But just proving that factoring is NP complete, or just proving that factoring can be done in polynomial time, doesn't do the job. You have to do both. Okay. Suppose you found an O of n to the 100th algorithm for solving the subset sum problem, where n is the total number of bits required to represent the set. What would this imply? Would it imply P equals NP, P is not equal to NP, or neither of the above? Okay, what's the argument for A? Yeah.
Subset sum is NP complete and the algorithm is polynomial.
Right. So that would prove P equals NP. This would mean that you've proven that a NP complete problem can be solved in polynomial time. So that would prove P equals NP. Okay, let's take a quick break and we'll look at the rest of it. Okay. If it were proven that every algorithm for solving the Hamiltonian cycle problem on a connected graph must be omega of 2 to the e in the worst case, where e is the number of edges in the graph, what would this imply? Okay. First of all, is e a measure of the size of the problem?
Not necessarily.
Okay. Why do you say that?
Because E is kind of dependent on V. Like, this is a connected graph, but theoretically E could be 0 or it could be V squared.
Okay. But there is a relationship between E and V.
Yes.
So E is somewhere between 0 and V squared. Okay? So how does that factor into the solution here?
Well, this is a connected graph, so we know E can't be 0, and
All right.
it's at minimum V.
Okay, so it's a connected graph. When you represent a graph, what's the size? Okay, it's either going to be V squared if it's an adjacency matrix, or it's going to be E plus V if it's adjacency list. Okay, and it's connected, so we know that E is roughly greater than or equal to V. It could be like 1 less or something. So it's not the exact measure of the size, but it's proportional to the size. It's quadratically proportional to the size. So you can think of E as a lower bound on the size of the graph. Right? E is a lower bound on E plus V, and it's a lower bound on V squared. So the graph is at least E bits big. So what does it mean then if you prove that any Hamiltonian cycle problem must be O of 2 to the E? So that means it takes exponential time. So dealing with a graph with E edges is going to take exponential time. And what does it mean if an NP-complete problem requires exponential time? Yeah, P can't equal NP because that's another exponential time algorithm. Yeah,
Did you start recording again?
I did. But I always lose my confidence when I'm asked. So. Yep. Okay, so just this is another. It's a lot like the factoring one. This would be discovering that some NP-complete problem, that some problem from NP requires exponential time. Okay, suppose A and B are search problems, and A is known to be NP-complete. You want to prove that B is also NP-complete. Which of the following should you do? Okay? Do you reduce the known NP-complete problem to the candidate NP-complete problem? Yes. I told you that would be on the final. It's always on the final, something like that. So just keep that in mind. If you're trying to do a proof of NP-completeness, you reduce the known NP-complete problem to the one you're wondering about, not the other way around. Yeah.
So you mentioned that the discussion between like P does not equal P equals NP is still like open, right?
Yes.
So that also means that there hasn't been a proof of any of the NP-complete to be exponential.
That's correct. Yeah, that would solve the problem. So if someone did that, that would resolve the problem. It would show that P is not equal to NP.
But there are problem sets that have been proved to be exponential.
Oh yeah. Yeah, but all the problems that we know require exponential time are not members of NP. Yeah.
So what would satisfy like a neither of the above case?
What would satisfy what?
Neither of the above, like C, in that question. Would there be any case that would satisfy?
I mean, you're asking what question could I ask where the answer would be neither of the above?
Yeah.
You find a faster way to sort.
Oh, okay.
You prove that factoring can be done in linear time in the size of the number. So you find a polynomial time algorithm for a problem from NP that previously did not know an algorithm for. And that wouldn't change that would be neither of the above as long as that problem wasn't NP complete. If you found a fast algorithm, found a polynomial time algorithm for a known NP complete problem, that would prove P equal to NP. Okay. Modular equations. All right. So what can we multiply 5 by to get 2? I'm working mod 7. So I just start thinking about 7, 14, 21, 28. 28 is 2 less than 30. 5 times 6 is 30. So I say 6. Is that right? All right. We want x times x to be 0, mod 8. Yep.
I think the directions say it can't be 0.
Yeah, the directions say it can't be 0. 0 would work, but it says x must be positive. But 4 times 4 is 16, and 16 is a multiple of 8. So, and then the inverse of 7, mod 11. So you're looking for a multiple of 7 that's one more than a multiple of 11. Seven, 14, 21, 28, 35, 42, 49, 56. 55 is a multiple of 11. It's easy to recognize multiples of 11. So that'd be 8. 8 times 7 is 56. That's one more than multiple of 11. Question?
So just to clarify, the bottom one is saying the same thing as the true problem.
Well, it's the same kind of question as the first one. There also, no, never mind. Yeah. If this said 5x is 1, then we're looking for the multiplicative inverse of 5, but we're not there. We're looking for something else.
So you
Yeah.
can rewrite it 7 times x equals 1 mod 11.
Yeah, I could have asked this question here as 7 times x equals 1 mod 11.
All right.
Okay, and again, I think I've said this before, that it's always a sad sight to see students spending 15 minutes using the modular multiplicative inverse algorithm on paper to try to solve something like this. That's never my intention. The idea is to sort of solve it like I just did. You just got to recognize that you're looking for a multiple of 7 that is 1 more than a multiple of 11. And then you just start enumerating multiples of 7 until you realize you've gotten one. And you only have to consider 10 multiples of 7. It has to be somewhere. The answer has to be less than 11. So. Okay. So this is RSA, electronic commerce rather. So there are 4 steps. There's a step where you encrypt something with an AES key. There's a case where you encrypt something with an RSA public key. There is a step where the browser requests a digitally signed certificate, and a place where the browser decrypts something with an RSA public key. Okay, so this is all happening in the browser. So just imagine you've got Amazon and you've got browser. And we're supposed to put this in order. So when you're doing electronic commerce, trying to do secure communication, what's the first thing the browser wants? It wants Amazon certificate. So first thing it's going to do is C. It's going to request Amazon certificate. So Amazon certificate comes over. Now, what's the browser going to do with certificate? It's going to verify it, which means what? Yep.
It's gonna like encrypt something on the AES.
Well, that's not verifying. How do you verify a certificate? It really came from Amazon.
Do you decrypt it with the RSA?
Right. So you decrypt it with the public key. So basically, the certificate will have been signed by some organization like VeriSign with their private key. So it had been encrypted with their private key. The browser contains the public key for VeriSign. And so you decrypt the certificate with the RSA public key to establish that this really was signed by VeriSign. So that's D. Now what's the next thing the browser does, now that it knows it really has Amazon certificate? Okay, so now it, let's see, CD. So it encrypts something. What does it encrypt with the RSA public key?
The AES key.
Right, so it generates an AES key and encrypts it and sends it across to Amazon to use. And so that's step B. And then finally, Amazon will respond with something encrypted with an AES key that the browser is going to have to decrypt. So that's how that works. Any questions about that? Start back there. Yeah.
Can I expect us to remember all the modulus for RSA and the rates top denominator and all this actual math that happens to it?
Yeah, you should know the algorithm for the algorithms for RSA. Yeah. Key generation, encryption, decryption. Yeah.
So why do you apply the RSA public key first and then the AES key? I thought it was the other way around.
Well, there are two things we're doing with keys. So the first thing we have to do after we get the certificate, we have to make sure the certificate is valid.
Right.
So the certificate claims to have been signed by VeriSign, claims to have been encrypted with VeriSign's private key. So we got to make sure. So we decrypt it with the public key. That's the verification step. Now we have Amazon's public key. That's what's in the certificate. That's what we carried it out. And so the next step is the browser generates an AES key to use during the session and has to send it to Amazon. So it sends it by, securely by encrypting it with Amazon's public key.
Wouldn't that be A then instead of BA?
Yeah.
No. You think it should be A and then B? Well, first thing it's doing is it generates the AES key. It doesn't encrypt anything with it. It just makes an AES key, picks an AES key, and sends it to Amazon to use. doesn't use the AES key. It can't use the AES key to encrypt anything until it has sent it to Amazon. And to send it to Amazon, it has to encrypt it with with Amazon's public key. Now both sides have the AES key and can start communicating. Or am I completely missing something? Yeah.
We just confused because in our networking class we use both in the same set, so we send a message encrypted by the AES, and then we also encrypt the key in the same set.
Okay.
That's why.
I mean, I guess in theory you could, you got to do two things. Your goal is to have both sides have the AES key so they can communicate. And Amazon can't do anything with anything encrypted with the AES key until it receives the AES key. So I'm thinking of, we send, first thing we got to do is send that key to Amazon. Then we can start talking. Any other questions? Okay. You need an algorithm that can find the k smallest elements in an unordered array of n integers. Give a tight upper bound on the expected running time for both of the following algorithms. So what does it mean that, okay, you got two variables here, k and n. K is the number of elements you want, and n is the length of the array. So you sort the array using quicksort, and then you copy out the first k elements. So what's the complexity of that? What's the complexity of the sort? N log n, on average, and then the cost of copying out, which is k. But k is smaller than n, so this is going to be O of n log n. Okay? What about using quick select to find the kth smallest element? Okay? What was the average case running time of quick select? Yeah, that's linear. So it would take O of n to find the kth smallest element. Now we use this element as a pivot and partition the array around that kth element. So we're going to have elements smaller than the kth element, and then the kth element, and then the elements larger than the kth element. What's the complexity of partitioning? That's also n. And then we got to copy out the first k elements, which is k. And so this becomes O, this is just O of n. And what's the difference between two algorithms? Right, one completely sorts. So the first one, with a quick sort, you're going to get the first k elements in sorted order. What are you going to get out by the second one? You'll get out the k smallest elements, but they won't be sorted. The largest one will be last, because that'll be the pivot. The other elements will be scrambled. But you weren't required to get the k smallest elements out in sorted order. So we're sort of paying a price to give an ordering that wasn't required. Okay. All right, you've seen one of these before on the midterm. So we know f is O of n squared. We know g is O of n cubed. What does that tell you about the relative sizes of f and g?
F is big O of G.
Okay, it's tempting to say f is big O of g, but why is that not right? O is just an upper bound. F could be n squared and g could be n. And both those statements would be true. Or vice versa. So this is neither. Okay? What if you know that f is O of n squared? And in fact, let's skip down to the third one. Now, the third one's the same as the first one, except now we're using thetas. How does that change things? We know that f is n squared, some sort of n squared, and g is some sort of n cubed. So this definitely tells us that f is O of g. There's always someone any exam I give that gets this perfect except everything's backwards. Right? They meant to write F as O of G, but they write G as O of F, and they do that consistently in every question. So don't get it backwards.
So,
Yeah.
on the first one, you said neither because, like, that's an upper bound.
Yeah.
G could end up being a lower than F, right?
Right.
So, on the third one, G is
Oh.
bounded above by.
Oh, that's an, see, I read that as a theta.
Okay.
Dang. Okay. See, I never make 100 on my tests. So. Let me try again. So if they were both theta, I would be right.
So the fourth.
Oh, the fourth one. You're right. Fourth one is. Maybe the fourth one. That's my claim. I was looking at the fourth one. Okay. Oh, okay. In my defense, when you said the fourth one, I just looked at that symbol. All right, so you gotta read more carefully than me when you do this thing.
Good luck explaining that to the professor.
Yes. All right. Let's just go to the second one here. All right. F is O of n squared. So you know it's n squared or better. And G is omega of n cubed, meaning n cubed or worse. So what gives? What can you say?
F is big O of G.
Right. F is definitely big O of G because. Yeah. All right. This was the first one I messed up. So F is definitely some sort of n squared, but G could be n cubed or could be smaller. So what's the answer? Neither. And in the last one, we know F is an n squared type of thing and G is an n kind of thing. So G is big O of F. Yeah. Thank you for your help. Okay, any other questions? Let's see how, we're getting close. No, we're not. Okay, suppose that you have a rope that is n meters long and contains n knots. You want to cut the rope into the smallest possible number of pieces such that no piece has 2 knots that are more than 1 meter apart. So how would you approach this? Is this a greedy algorithm, a dynamic programming algorithm, a divide and conquer algorithm? Okay, so what would be the greedy algorithm? What's that?
You cut it after you see a knot.
Okay, you want the smallest possible number of pieces such that no piece has 2 knots that are more than 1 meter apart. So you don't want to cut it when you see the first knot. What do? You move from one end, you see a knot, what do? You keep going and you see, you keep going, okay, it says no 2 knots are more than 1 meter apart. So you would keep going until you got to a knot that was more than 1 meter from the first knot and put the cut right before that knot. And then you sort of repeat the process. But it would be definitely, you don't have to describe the algorithm, it'd be a greedy algorithm. There's no need to try all the possible places to make the cut. You just, that's easy to do greedily. Okay, suppose that a weighted, undirected, connected graph contains V vertices and V log V edges. Give a tight upper bound on the time complexity of Dijkstra's algorithm on such a graph. Okay, so to do this, you need to know the complexity of Dijkstra's algorithm. And what was it? It's V plus E log V. Okay, so how do we put all this together and come up with a solution? Yeah. Right, so we plug V log V in for E, we get V plus V log V log V, and if we simplify that, What will it simplify to? Yeah, v log v log v. All right, I really like this problem here. So let's do it. You're commander of an army. At 8 o'clock, you intercept an encrypted message intended for the enemy commander. It's encrypted via RSA using the commander's public key. You know the public key, but you don't know the secret key. The key pair was constructed using massively long bit prime numbers, really military grade. Your spies have determined that the original message was either attack from the east at noon or attack from the west at noon. Is it reasonable to expect that your encryption specialist will be able to figure out what the original message was in the 4 hours remaining before the attack begins? Okay? So, what if your strategy was to try to decrypt the message by factoring the, you know the public key, so you know in. Think you can factor it in 4 hours to figure out what the secret key is. That's not reasonable. Nevertheless, you can figure out the original message. How? Yeah.
Encrypt both of the message you think it is and compare
Right. You know it was one of 2 messages, so you just encrypt them both and see which one matches the encrypted message you intercepted. So, if you know something about what was encrypted, then that's easy to do, so I guess the answer is yes. Okay? So doing this, I've always told students when they complain that my questions are tricky, I always say, no, they're clever. But I have to admit some of these are tricky. So. Oh, this was awful to grade. Okay, we'll do this one, and then so what Bobby will be doing a review tomorrow at 10:30 in here, and he had planned to go over another exam, but I'll have him finish this one first. Okay, I want to determine whether a string S consists of a sequence of English words. For example, black and blue does, but black and BLE does not. So here's a greedy algorithm. If the string is empty, you report true. Yeah, it's a sequence of 0 English words. If S does not begin with an English word, report false. Otherwise, remove a word with which S begins and return the result of running the algorithm on the reduced version of S. Okay, does that work or not? Well, it doesn't. What's a string it doesn't work on? So the idea is you scan it looking for a word, and when you find one, you take it off, and then you solve the problem on the shorter one. So, yep. So P. Okay, pies. Okay, so why wouldn't that work? Why wouldn't the algorithm work here? Okay, pies, the answer should be true. That's a sequence of 1 English word. But the greedy algorithm might go along and say, okay, PI, that's a word. Or if you don't believe that's a word, PIE is a word. And then it would throw that out and then ask whether what's left is a sequence of English words, and S by itself or PS by itself isn't. So, why was this such an awful question to grade? Every answer was different. They're like effectively an infinite number of correct answers. So it's like the worst possible grading scenario. Okay, the question goes on to talk about a dynamic programming algorithm, but we'll let Bobby finish that. So anyway, that wraps it up. Our exam is a week from tomorrow, so I'll see you then. A week from tomorrow. A week, that's right, a week from tomorrow. Yeah, we plan to report it.
Oh, that's awesome. That would really help. Thank you.
Yeah, I realize that would be an issue. So.